In this talk, I will present dynamic iteration schemes by convergence rates and error bounds. The outline of my talk is the following. In the first part, I will introduce dynamic iteration schemes and I will apply them to different kinds of semi-discrete systems. These will be systems coming from pseudospectral and finite difference semi-discretization processes applied to PDEs. And then in the next part, I will talk about different convergence rates of different numerical algorithms based on the dynamic iterations. Then I will introduce error bounds which are derived for the dynamic iterations, and these error bounds will involve non-constant coefficients. Then I will introduce transformations that accelerate the convergence rate of dynamic iteration schemes. And then in the next part, I will present results of numerical experiments. And finally, in the last part, I will finish by conclusions and will sketch future plans. Dynamic iterations are different than static iterations because they are applied to systems of differential equations, while static iterations are applied to systems of algebraic equations. Another difference is that static iterates are just standard vectors which don't depend on time, while the dynamic iterates are time-dependent vectors. And this brings the advantage that the application of implicit time integration methods to PDEs is straightforward if dynamic iterations are involved and applied as an intermediate step. Another advantage is that we can use paracomputing environments if we apply dynamic iterations. And these two figures present the errors of the dynamic iterations as functions of iteration index. So the horizontal axes are for the numbers of iterations, while the vertical axis are for the errors. And here the left-hand side figure is prepared when dynamic iterations are applied to pseudospectral semi-discrete systems used for the heat equation, while the right-hand side figure is prepared when dynamic iterations are applied to the finite difference semi-discrete systems used for the same heat equation. Now, the ranges of the vertical axis in both figures are the same to compare errors. And we can see that the dynamic iterations preserve the accuracy of the semi-discretization processes. And we also see that in the left-hand side figure, we get such a nice improvement in the accuracy by increasing the number of grid points by only 2. Here, capital N stands for the number of spatial grid points. We also see some improvement in the accuracy in the right-hand side figure, but this improvement is not as good as in the left-hand side figure. And this is because of the well-known fact that pseudospectral methods have much higher accuracy than finite difference methods. However, it turns out that there is another advantage, and the other advantage is that dynamic schemes converge in much less numbers of iterations when they are applied to pseudospectral rather than finite difference semi-discrete systems. And this is observed here using the horizontal axis. Now the ranges of the horizontal axis in both figures are completely different. The range of the horizontal axis in the left-hand side figure is from 0 to 50, while the range of the horizontal axis from the right-hand side figure is from 0 to 3,500. And here, for example, the best accuracy from the left-hand side figure represented by this short line segment this was obtained only after 40 iterations, and this accuracy is about 10 with minus 10 as a power. While the best accuracy from the right-hand side figure is represented by this short line segment. This is about 10 with minus 3 as a power, and this accuracy was obtained after 3,000 iterations. Here we observe such a comparison between 40 and 3000 iterations, which is a huge difference. And now the goal is to investigate the reason why we get such a huge difference in the numbers of iterations in these two cases. In order to investigate this reason theoretically, we need to introduce some notation. And if we consider this initial boundary value problem written in this form labeled by 1 with the heat equation, and then if we apply the finite difference spatial discretization, we get such a system of ordinary differential equations written in this form labeled by 2. Now, after the application of dynamic iterations to this system 2, we get this simpler system. This is written in this form labeled by number 3, and this is a simpler system because here we use the present iterate denoted by the upper index k plus 1 only for the main diagonal, and the other non-zero of diagonal entries are not multiplied by the present iterate. Instead, they are multiplied by the previous iterate, denoted here by the upper index k. So this is a diagonal system because it's an iterative process. In the case of pseudospectral semi-discretization, we get completely different differentiation matrices. These are now dense and lower dimensional matrices, and for example, for the heat equation, we use such a second order differentiation matrix denoted here by the upper index 2. The entries of these matrices can be computed using the well-known algorithm by Thornberg from 1988. Now, using such a matrix, we transform the heat equation into this system of ordinary differential equations written in this form labeled by equation number 4. And after the application of dynamic iterations to system 4, we get system 5 written down here, which is a simpler system because again it's a diagonal system, and here the present iterate vk plus 1 is multiplied only by the main diagonal entries, and the other entries of the differentiation matrices are not multiplied by the present iterate, they are multiplied by the previous iterate vk. So this is a diagonal system, and now if we apply these Jacobi dynamic iterations to the finite difference semi-discrete systems, then we can derive these two error bounds written in this form labeled by number 6. And here we derived the first one in the infinity norm, while the second one is derived in the Euclidean norm. In the case of the application of these Jacobi dynamic iterations to the pseudospectral semi-discrete systems, we derived such different error bounds written down here in this form labeled by number 7. And again, as before, we derive the first one in the infinity norm and the second one in the Euclidean norm. Here, these four constants, R1, P1, R2, and P2, are determined according to the choices of the pseudospectral differentiation matrices, and the error bounds written in the form labeled by 7 are much smaller than the error bounds written in the form labeled by 6, and they converge in much less numbers of iterations than the error bounds in 6. So we conclude that dynamic iterations don't depend on the number of equations, but on the parameter values, specifically on the magnitudes. And now the next goal is to use substitutions that decrease the magnitudes of the parameters. In both cases, for finite difference and pseudospectral semi-discretization, and in many other applications, we get systems written in this common and concise form, written labeled by equation number 8, where capital A comes either from finite difference operators or from pseudospectral differentiation matrices. And now, having this matrix A, we use this substitution written in equation 9, which decreases the magnitudes of the entries multiplied by successive iterates. Here, alpha is an approximation to an eigenvector of the transpose of A, and having this new dependent variable zt, we get this new system, system 10, where the unknown solution y involves zt as the first component. We now split this matrix B into B1 and B2, where B1 involves the main and lower diagonals of B, and B2 involves the remaining entries of B. Then we use the iterations written in this form down here, form 11, where the present iterate is multiplied by B1 and the previous iterate is multiplied by B2. We also use the same splitting of the matrix A, and we create an equivalent iterative scheme with the splitting matrices A1 and A2 as counterparts for system 8, where the successive iterates are denoted by xkt. So like in 11, the present iterate is multiplied by A1 and the previous iterate is multiplied by A2. Now, running numerical experiments for both schemes, we get numerical errors presented in the next slide. And here the numerical errors for both numerical schemes with and without the substitution involving the function zt are presented in these two figures respectively. The left-hand side figure presents the errors for the system without the substitution, while the right-hand side figure presents the errors for the system involving the function zt from the substitution 9. And in both figures, the errors are presented as functions of the iteration index. So the horizontal axis in both figures are for k, and their ranges are from 1 to 40. Also, the errors in both figures are measured at the same fixed value of time t equals 10. From the left-hand side figure, we see that the scheme without the substitution converges in 30 iterations, while the scheme based on the substitution and presented in the right-hand side figure converges in only 8 iterations. So by using this substitution, we save 22 iterations, which of course saves computational time. Now, the range of the vertical axis in both figures is identical, so that we can compare the accuracy of both numerical schemes. And the accuracy ranges from about 10 with minus 6 to 10 with minus 9 as a power. And we see that the substitution involving the function zt preserves the accuracy of the time integration. So the conclusion is that by reducing the number of iterations by 22, we save computational time and we reach the same accuracy in both cases. The accuracy for different values of time is presented in these two figures. Now the errors are presented as functions of t over the interval from 0 to 10. So the horizontal axis are for time and the vertical axis are for the accuracy. The left-hand side figure presents the errors for the numerical scheme without the zt substitution for k equals 30, which is exactly the number of iterations at which the scheme converges. And now the right-hand side figure presents the errors for the numerical scheme with the ZT substitution for k equals 8 over the same time interval. So the ranges of the horizontal and vertical axis are the same in both figures, and the curves of the errors are very similar in both cases, in both figures, with and without this ZT substitution. So the conclusion is that the application of the new second iterative scheme preserves accuracy, and at the same time we get the solution after only 8 iterations instead of 30 iterations, which saves computational time. Now let's summarize all conclusions together. The first conclusion is that the dynamic iteration schemes converge in significantly less iterations when applied to pseudospectral rather than finite difference semi-discrete systems. Then another conclusion is that implicit integration applied to dynamic integration schemes is straightforward, and there is no need to solve algebraic systems per each time step, no matter if it is for linear or nonlinear systems. Then the next conclusion is that dynamic iterations don't depend on the number of equations but on the parameter values. And finally, we proposed new schemes based on substitutions which decrease the parameter values and thus accelerate the convergence of the schemes. Now, we currently work on dynamic iteration schemes applied to systems of delayed differential equations, and we also apply these schemes to the Wilson-Cohen model coming from neuroscience. This is such a model written in this form as this PDE, where we have such an integration on the right-hand side with over the spatial domain D, where the spatial variables are 1, 2, or 3-dimensional. And we also plan to derive error bounds in discrete cases. Now, using my last slide, I'd like to thank you for your attention.